In the previous class, we were discussing about classless addressing. Today, we will see in classless addressing, we will consider the topic of subnetting. Okay. So when we actually consider this one, like what is the difference we are going to have it? If it is classful addressing, directly we will come to know what is the default mask, and from that we can calculate what is the mask we are going to have for subnet. Okay. Similarly, we will be finding like subnet address, that means the starting address in that particular subnet. Okay. And we also have variable length subnets, but if we consider classful addressing, it's like if I consider class B, and if I am making some 4 groups, 4 different subnets, it will be like each group is going to have 2 to the power 16 divided by 4. But when I go with this classless subnetting, I cannot exactly say like this. Okay, it all depends on how many subnets we are making and what is the prefix we had before that. Okay, everything depends on this particular thing. Okay, so that is the variation. Procedure and all remaining things are same. Okay, so there we used to have default mask using which we used to find the network address. Here we are going to use subnet mask using which we are going to get subnet address. Okay, that is the difference. So in fixed length subnetting, the number of subnets is a power of 2. That means if I go with class A, class B, class C, I can have either 4 groups, 2 groups, 8 groups, 16 groups, like that I need to have. I cannot have something like divide into 3 subnets or 11 subnets or 10 subnets, like that we cannot have in classful address. That is the first thing we need to consider. Then let's go with an example. An organization is granted the block. This is the block they are saying. Okay. If this 26 is not there, I can say like this is class B. Okay. And I can easily make 4 subnet out of that one. Okay. Starting from this is class B means I am going to have 130.34.0.0. This is what I will be having. From that we will start and we can consider 4 subnets. So it will be like it will get till 130.34.63.255. Then 64.0, 127.255, then 128.0, third one, then 191.255, then 192.0, 255.255. Like that we can consider if it is class B. Okay, but we are not saying this is class B, but the suffix, whatever the prefix value we have, that is 26 n value. So how many addresses are there in this particular block? How many addresses? 246, exactly. So 246 means 64. Okay, so only 64 addresses are there, and we are dividing into 4 groups. So we are going to have each group will have 16 addresses. Okay. Now for this original block, I need to find what is the starting address. So how I can find starting address? Using mask. What is the mask in this case? (26 bits), right? 26 means 8 bits we need to consider here. 8 bits, 8 bits, 2 bits. Correct? Okay. So I'll have 130 here, then 34, 12, and here 2 bits means 64. We will be writing 01000000, and I need to consider first 2 bits as it is, right? So that will be 64 only. Okay. So what is the subnet prefix length? Subnet prefix length is 26. Okay. And okay, we are just finding that one. We will see in the next slide what else they are asking. Okay. So actual organization, it had a prefix length is 26. Subnet prefix means after making into 4 groups, what is the prefix you are going to have. So how we can find? Same formula. We used to have log n base 2, right? Here n is 4, so this value will be 2. So 2 we need to add to 26. So we will be getting 20. So if it is class B, we used to have 16. 16 plus 2, 18 we used to write. But since this is CIDR and the actual value of n is 26, after making subnets, it will be 20. Okay. Then what are the subnet addresses and the range of addresses for each subnet in the previous example? So we considered 130, 34, 12, 64, right? 130, what is the next one? 34, 12, 64 by 26. That is what we have, right? Okay. So this is the starting one. Okay, when I consider the last one, total how many addresses we said? 64, right? So what will be the last address in this case? To get last address, what we need to do? Number of addresses minus 1 we need to add. Number of addresses is 2 power 6 means 64. So we need to add 63. Okay. So if I add 63 to this, I'll get 130.34.12.127 by 26. So this is the group I have, and I need to make total 4 groups out of it. Okay. So the first one, like each group it will have 16 addresses, right? So if I start with this one, okay, what will be the last address? Each group has 16 addresses. So to get the last address in first group, what I need to do? How much I need to add? 16. We are going to have 16 addresses in each group. Here if it is 64, what we are doing? We are adding 63. 15 we need to add, right? So if I add 15, the first group will have 130.34.12. If I add 15, it will be 79. Okay. First subnet is starting from this value, ending at this value. Okay. Second subnet, it will start at 130.34.12.80. Is it correct? Okay. And again, if I add 15 to that, it will be 130, then 34, 12, 95. That is the second block. Third block, similarly, 130, 34, 12.96, 130.34.12. That if I add 15, what will be the value? 111. Okay. Next, fourth one, you are going to have 130.34.12.112. If I add 15, it will be 127. Is it clear? Yes. Okay. And this is not complete. We need to represent the subnet prefix also. Originally we had 26. When I go to this, it will be how much? 28. Right? Similarly, here also we need to write /28, 28, 28. Okay. Is it clear? Okay. So the entire thing is here. So we are starting here 64 and 79 is the last one in this group. Then 80 we are starting. 95 will be last in this one. From 96 we are starting here. 111 will be last year. From 112 we are starting here. 127 will be the last one. Like that we have made 4 different groups. Is it clear? Okay. Any doubts? Okay. And also you can see we are writing 28. Original network it had 26. When we get on to individual networks, 4 different things, we are having 28 here. Okay. Then, okay, the same explanation is here. Explanation for individual subnets. Then this is one of the example where we have variable length subnet. Okay, so I have this address. Total, how many addresses are there? If I say 24 as the prefix, hmm? 256. Okay, so 256 addresses are there. Out of this 256, what they are saying, we need to make 11 subnets. Okay, 2 subnets each with 64. Okay, out of this 256, I need 64, 64. That is one group. Okay, 2 subnets each with 32. 32, 32. Then 3 subnets each with 16. 16, 16, 16. Then at the end I have 4 subnets each with 4. Okay, so just count here whether we are getting 256 or not. This all, if I combine, it will be 16. Okay, this entire thing it will be 64. Okay, here 64, 128. At the top I have 120. 256. So this is how we are supposed to make. Okay, so how we will proceed? Earlier it was like I just had like equal length subnets. So directly I used to consider starting from the beginning. I used to write starting address, end address like that. But here we have variable things, right? How we can proceed in this case? Find the first address and 63. Okay, then okay. Okay, then in that case, can I go from this direction? First make these things, then these, then these, then this. Because the way you are progressing, I can also come from down, right? Okay, so about that one, we will address when we discuss the concept called as longest mask matching. Okay, what happens if I go with the bottom? We will address there. Okay, now whatever may be the thing, how I can do is, okay, let us consider this plain one. So what we will do is, I have 256 addresses. Okay. Let me also write the starting one 14, 24, 7. 14, 24, 24.0 by 20, 24. Okay. Okay. So this is what I have. So we will consider like 256 addresses are there. So first, what I will do is, I will divide these things into 464 groups. Can I make like that? Okay, then it becomes equivalent, right? Okay, this will make my first requirement. 2 subnets each having 64. To get the second requirement, this 64 I will make into 32, 32. That will meet second requirement. Third requirement I need 16s, 3 16s. So what I will do is, I will take this one into 4 16s. Then if I go with this one, third one will be satisfied. From here, I need to make 4 cores. Okay. So this is the procedure. Okay. Now for this 26, what is the prefix we had? 24. When I go with 64, 4 groups means extra 2 bits we need to consider. So it will be 26. Here for 32, how many we are making? 2 groups. What did we have for 64? 26. For 32? Increase or decrease? 27. Okay. Then for 16? 29. Why? 4. So how many we need to add? 2. To which one we will add? Why? We are coming from this, right? So for this 26 we will be adding and it becomes 28, right? And for these things, 30. Okay. So is it clear? The prefix part is clear. 24 we had, 26, 27, 28, 30. Okay. Now we will go back to the previous slide. Okay. So first we are making 64s. Okay. So starting is 114.24.74.0. So first one starting at that position. Where it will end? It will end at 63, 74.63. So second one is starting at 63. Okay. And what is the prefix I have? 26. Here also I have 26. Okay. So the next 2 things, whatever we have, okay. It's like these 2 64s, if I consider, it will start at 128, end at 191. Okay. And this one will start at 192 and it will end at 255. So we will consider this one first. Okay. So it is starting at 128. Okay. It is starting at 128. I need 32 addresses. So I need to add 31 to that. Okay. So 31 I will add. So what it will become how much? 159. So next one, where it will start? 160. So it is starting at 160. Where it will end? 191. Okay. So next one, it has to start at 192. And how many addresses here? 16 addresses. Like that, 3 groups. So how much we need to add? 15. So when I add 15 to this, it will become 207. Okay. 208 is the next one. Add 15. It will be 223. So 224 is the next one. From this, again 15 if I add, it will be 239. So next group it starts at 240. Okay, 240 I have there. So here I am going to have 4. I need to add 3. 243 it will be last one. 244 I am starting here. 247, 248, plus 3, 251, 252, it will end at 253. Sorry, 255. Okay. So like that entire thing we will be getting. Okay. So the same thing we are describing. Okay. So it's just like how we are dividing. Okay. So we are just describing like how we will be getting 16. What are the prefix bits we have that. Okay. So overall, this thing is clear. Okay. So you just have to keep in mind from the original 256. First we are making 64 4. Out of the third one, we are doing with this 16. 16, 16. Sorry, this 32, 32. The remaining 64 we are making into 16s. After that, again we are making 4 different groups. Okay. So that procedure, if you remember, you can easily identify this. Okay. Okay. Similarly, we have another problem. Another example, assume a company has 3 offices, central, east and west. The central office is connected to east and west offices via private point-to-point wide area network lines. The company is granted a block of 64 addresses with beginning address. The management has decided to allocate 32 addresses to central office and divides the rest of the addresses between 2 offices. Okay. like what are the other we have? East and West. So East and West are going to get 16, 16 because we have total 64. Okay. So the corresponding figure you are going to have like this. So anyway, we do not have East and West highlighted over here. Anyway, the original one had 64 addresses. Okay. This network 128. So we'll start with this one. So first, the central office it was granted 32 addresses. Okay. So from this we need to add 31. So till 159 we are going to have for this particular thing. Okay. And east and west you are going to have two things. Then from 128 to 159 you are going to have here. Okay. 160 to, if I add 15, 175, I'm going to have one of the east or west, anything. Then 176 to, and if I add 15 to that, it will become 191. Till 191, I'm going to have the third one. Okay, that's it. Like basically, if you remember, starting and ending, we are not giving to any system, right? That's the reason till 158 they are showing here. 159 will be broadcast address. Okay. Then here they are considering from 160 and all the way till 174. 174. Okay. 175 also it will be broadcast address. So 176 they are considering as network address. Till 190 we can give to systems. 191 we will be using as broadcast address. Okay. So it's just like why they have represented dots is, if you see here, the central office is connected to east and west offices via private point-to-point wide area networks. Okay. So central office is connected to remaining two using point-to-point wide area network. Switch environments you are going to have something like this. Point-to-point you are going to have like this. Even you can specify here. This is point-to-point wide area network. Okay. Sorry, switch WAN means you are going to have like this. You are going to have a network. In between, you are going to have switches. Okay. And you will have connections like this. Okay. So like that, we are just representing that particular. Okay. And again, you can see here 26. It is made into like first we are making into 32 and 32. Two groups. Okay. 132 we are giving here, right? So number will be 27. And again the remaining 32 we are making into 16 and 16 two groups. So again we need to add 1 for 27. So we are having prefix 20. Okay. So it's just about how you are going with each block and how many bits you are adding to prefix. That is what we are interested in checking in these problems. Okay. Okay, the same explanation is given. Okay, so next thing is address allocation. In address allocation, for example, an ISP. What is ISP? Internet service provider. Okay, internet service provider is granted starting from this address. Okay, so for an ISP, they are granting 65,536 addresses, and the ISP needs to distribute these addresses to 3 groups of customers. And how it needs? First group has 64 customers, each having 256 addresses. Okay. 64 customers, each having 256 addresses. Second one, 128 customers, each having 128 addresses. Okay. Third one, 128 customers, each require 64 addresses. So we have to start with this one because always we go with more number of addresses. So starting from this number, I need to consider 64 blocks, each having 256 addresses. So if I need 256 addresses, what should be my prefix? 24, right? Because 256 is 2 power 8. I need to subtract 8 from 32. So it will be, we will be having slash 24. Okay. For this one, we will be getting that. This case, I need to have 128 addresses in each. Yes. 23 means I'll have 512. See, 128 groups are there. Each group should have 128 addresses. To represent 128 addresses, how many bits we need? To power how much? 128. 7. So what should be my prefix here? Yes, 32 minus 7. So I need to have slash 25. Last one, 64 addresses. 26. Okay. This part is clear, right? So we will start like each like 64. It's like 64 and that is 256, right? So total how much it will be? 2 power 6 and each block has 2 power 8. So total 2 power 14. Okay. So first group will have, starting from this one, we need to add 2 power 14. So 2 power 14 means I need to consider 14 ones. 14 ones means it will be 8, 6, 64 dot 60. So first block will have from 190 dot 100 dot 0 dot 0 to 63 dot 255. Okay, till that block you are going to have. How we will see. Okay, so first block will have from 0 dot 0 to 0 dot 255, right? Because 256 addresses. Second block 1.0 to 1.255. Third block 2.0 to 2.255. Okay, so like that we are going to have till 63.0 and 63.255. Okay, that will complete my first requirement. Second one, you are starting at like it is like 2 power 7 into 2 power 7. Total that many addresses. So again this one, how much? 2 power 14 itself. Okay. So again it is like for the starting, what is the starting address here? For the second group, it is 190.100.64.0. That is the starting. So it will go till 127.255. Okay. So first block it will be like 64.0 to 64 point. What is the last value? It's not 255 because 128 addresses we have. So it will be like 127. Okay. Next group, it will be like 64.128 to 64.25. Okay. Within a particular 64 block, you are going to have two here. 64.0 to 64.127, 64.128 to 64.25. Next 65.0 to 65.127, 65.128 to 65.255. Like that, we will have till 127.255. Okay. So like that we are going to have. Then the third one it will start at 128.0. Okay. 128.0 and each 128 block it is going to have 4 now. 128.0 to 128.63, 128.64 to 128.127, 128.128 to 128.191, 128.192 to 128.25. Like that we are going to have. Okay. So we will see this diagram. Okay. So see here, the first one, as I said, we are going to start from here and we are going to end at 63.255. Okay. So this one you can directly get by using 2 power 6 into 2 power 8. That means. Okay. Then 64.0 to 127.255. Then the last one 128.0 to 159.25. Okay. Again, this is like 128 into 64 we will be making, and it is like 128 means 2 power 7, 64 means 2 power 6. So 2 power 13. 2 power 13 means 31.255. So we are adding, and the remaining addresses it will be unused. Okay. And again, when I consider individual customer, we said like we need 256 addresses. So it starts from here, ends at 0.255, 1.0, 1.255, like that. The last group has this starting address. Okay. Similarly, we can consider individual blocks. Okay. So like that, an ISP will be granting different IP addresses. Okay. So the same explanation we have. Okay. So first customer, second customer in the first block, second group, again first customer. We can see here 0 to 127, 128 to 255. Okay. And if I consider the third group, we are going to have four such things: 0 to 63, 64 to 127, 128 to 191, 191 to 120, 255, like that. So, like in the previous case, we had this many addresses, allocated were this many, and these are the available addresses. So that is about like how are we going to have this address allocations. Okay, is it clear? Okay. Then we have the concept of delivery, forwarding, and routing of IP packets. So when I say routing of IP packets, we are not dealing with individual routing protocols here. Okay, but we will be addressing like it's like how a particular packet is forwarded. Okay, how we are going to look into routing. Okay, routing, by looking at routing tables, how are we going to decide? That's what we will be discussing here. Okay, about routing protocols, we will be discussing in unit 3, where we have unicast routing protocols, multicast routing protocols, like that. Okay. So we will see here what are the different types of delivery we have dependent on connection. Then what are the forwarding techniques we have in classful addressing? In classless, what are the forwarding techniques we have? How a particular routing table works, and what is the structure of router. These are the things we will be looking in this particular topic. Okay. So the first one is delivery, like connection types we will see, and direct and indirect. So when I consider this one, like this router is there and it wants to send some information to this host. We have a direct connection, right? Then this is direct delivery. Nobody is involved in between source and destination here. Then I can say this is direct delivery. Similarly, when this one wants to communicate with this also, we do not have any intermediate node. Then I can say this is direct delivery. Okay. I have this one where I am considering this is the source and this is the destination. I have intermediate nodes. So I cannot say when source is sending to destination, I cannot say it is direct delivery. It will be indirect delivery. Okay. So it's like this one will be sending to some router, and this router address is not same as destination router address. So this is indirect delivery. Again, this one is sending to this one. Same here also. It is not the final destination. So it is indirect delivery. And here to here, this router is sending to this. Okay. Both are in the same network. Direct connection I have. So it is direct delivery. Okay. So whatever may be the delivery you consider, you are going to have one direct delivery. Okay. So in the previous case, I had direct delivery. In indirect delivery also, I am going to have one direct delivery. So whatever the connection you consider, at least one direct delivery you are going to have. Okay. Then forwarding, like what are the techniques we have for forwarding? These we will see. So whenever we want to forward a particular packet, the first question arises is how are we going to decide forwarding techniques? Okay. So maybe I can say like I'll try to look into routing tables. Okay. I'll try to look into routing tables, but the question arises, what should be there in this routing tables? Okay. What information I want to consider here? So the first example is routing table based on route. Okay. So for example, if I want to go with the destination host B, whether I should consider entire path from source to destination. That means first I will go to R1, then to R2, then host B. Is this the path I have to follow? Or we have another things. Okay. This is just like if I am going from A to B, I am trying to consider all the intermediate nodes which are available. Okay. Then routing table for R1, if I consider for this one, if it has to go to host B, it says like I have to go to R2 first, then host B. So I can see like that. Similarly for at R2 also, if I consider if I have to deliver to host B, directly we can deliver. So like that, we are going to consider entire path from source to destination. That is routing table based on route. Is there any problem with this? Yes. Is there any problem? I'll have each and every detail, right? But the problem is, for example, if I have 20 entries, the amount of space required will be more, right? So like that, if I have hundreds of devices, for each device, if I have to keep like this, we are wasting unnecessarily memory. Okay. So that is the problem we are going to have if I go with routing table based on route. And also the problem is when I consider internet, I cannot exactly say what is the path I will be following because this source will have control on how I will be forwarding here. But when it goes to R1, R1 decides what is the path it has to select. Okay, host A will not have the details like how R1 has to send, right? Okay, it doesn't have any control in internet. If it is telecommunications, source to destination, we are going to establish a path and we can consider like this is the exact path we are going to consider. But in internet, we are not going to have any such formality. Okay, we are going to use connectionless service, which means I am not going to have a dedicated path from host A to host B. So I cannot decide what is the path I have to use, like what is the path packet will be choose. So that is the problem we have. Then we will see. I will consider based on next hop. Okay. So if I have to go from host A to host B, I will contact R1 or I will forward to R1. That's what we are saying. If I consider R1, it says I will forward to R1. If I consider R2, it says like I have the direct network connectivity, so I will give it to the network. Like that, we are going to have. So this looks like it's fine. Okay, we will also see what are the other possibilities we have. Then I have a network specific method. Okay, so in network specific method, you are going to have like this. In host specific method, you are going to have like this. Okay, so the previous one, this is next how. Okay, the other method is host specific. If I have like this, in this network, I have A, B, C, D like this. Okay, so what I am saying, if I want to go from here to here, I have entry for A, I have entry for B, I have entry for C, I have entry for D. Okay. So it is something like I want to send a letter from Delhi to Hyderabad. Okay. And we are saying like I will have detailed address of each and every flat in an apartment. Okay. When I am referring from Delhi to Hyderabad, if I have just pin code, that is enough for me, right? I don't have to go in detail. Okay. If I refer to that, again when it comes back to Hyderabad, they will look at these flat addresses and apartment detail, right? Delhi to Hyderabad, I just need to look at pin code. Okay. I don't have to get into details of this. Okay. If this person has the in detail information, that is fine. But you don't have to have all four addresses there. Because what happens, you just consider in Hyderabad itself, I'll have at least 1 million devices. Okay. Similarly, Bangalore, I'm going to have 1 million devices. So if I need to keep an entry for a routing table here, I need to have my 1 million devices. Similarly, Bangalore 1 million devices information I need to have. So just for two cities, I'm going to have 2 million entries in routing table. So you just consider 1 microsecond for each of this entry. Okay. So 10 power 6, sorry, 10 power minus 6. and each city I am considering 10 power 6 entries are there. Okay, so when I consider for each city I am going to take 1 second gap. Like that, in the entire world, if I consider some 1,000 cities are there, 1,000 seconds. So how much time it takes? Okay, if you just imagine, okay, so let us consider instead of 1,600 seconds, that means 10 minutes. Just to look at your routing table, if you are taking 10 minutes, okay, so when you will be sending a packet? When we move to 5G, fifth generation communication, right now we are yet to achieve complete 4G, but in the entire world, people are talking about 6G. Okay, you can just think how technology is forwarding. Okay, still in India, we are struggling to achieve 4G. Okay, but people are working on 6G. Okay, so 5G has come. Some of the countries has implemented. Still, we have not completed 4G itself. Still, there are places where we are still using 3G. Okay, even in Hyderabad, I can say we won't get complete 4G. Okay, we will be using 3G itself. Okay, so when I move to this particular place, we are talking about ultra reliable low latency communication. We call it as URLLC, where we talk about delay of less than 1 millisecond. But how much time we are taking here? 10 minutes. Just to look at the routing table. Like that, how many routers will be there? So if I consider how much will be the time. So by considering all these things, we are saying that host specific method will not work for us. Okay. Instead, we need to go with network specific method. Okay. So I will say, like, if I have to go from S to A, I will contact this particular router. Destination, I will say like it is N2, and when it reaches R1, R1 will look at that particular information, so that I can try at least achieving this one. Okay, so that is the requirement. So for example, when we move to this 5G, we are talking about mission critical services. Mission critical services means, for example, driverless car is there. Okay, so driverless car, it will be moving. Suddenly, if it sees some obstacle, immediately it has to take response. It's not. It won't be like I'll send the request. I have detected some obstacle. What should I do? Like that question will go. If you take 10 minutes to get response, by the time you would have hit that particular obstacle, right? So we expect to have this kind of things, and these kind of things are possible only if I go with this kind of. I'm not saying like that is possible because of this, but I'm saying when I consider that we cannot go with these kind of host-specific routing tables. Okay, so in each and everything, like processing a particular packet, looking at routing tables, each and everything, we will have to reduce the amount of time we are spending. Okay, so that is not possible, and this is one method which is good. Okay, so host-specific routing, like routing table for host A. If I consider host B, if I have to go to host B, it says I need to contact R3. If I have to go to N2, I'll contact R1. If I want to go to N3, I'll contact R3. So like that, like there are some cases where some of the routers wants to implement this host specific method. In that case, we will be specifying like this instead of specifying network specific method. Okay. Then this is the default routing, like how exactly we are going to have routing tables is. We are going to consider like this. We will say entire network. What is the next hop? Okay. So this is the routing table for host A. Host A, if it has to go to N2, it will contact R1, and it knows only that one. After this router, whatever I have rest of the internet, it has no information. Like what devices are connected after that particular router, it has no information. So what it will do? If it doesn't find any others in this particular group, okay, it will send to default router. Okay, I am saying like here I have some address 500,008. That is the pin code of this block. Okay. And if I have anything else, I will be going this particular path. Okay. So we are not saying like the address is not at all available. If the address is available, that will be on that particular link. So to go to that, I will be contacting R. Like that, we will be using default route. Okay. Next comes how we are going to forward a particular packet when we consider classful address. Okay. So this is some method how we will be getting forwarding a particular packet. So first, whenever you get a particular packet, okay, let us consider like your router has received an IP packet. What it does is it extracts destination address. Okay, so what is the destination to which you want to reach? Once I extract that one, I'll check out what is the class of that. Okay, if that is class D or E, I will bypass this one. Okay, but if it is class ABC, I'm going to look at what is the network address. Because if I look at class A, I can easily find what is the starting address. If it is class B also, I can find. So by finding what is the class, we are going to find what is the starting address. Because in the routing table, you are going to have network address, right? We are specifying network address, how to reach that particular network address. We are not specifying individual host addresses. Okay. So we are trying to find what is the network address. Once I get network address, I am searching the table to find where that network address is there. Okay. So this is the procedure we are going to find. And to search this table, we also need some of the parameters. Okay. So for that, we might be contacting this ARP also. Okay. About ARP, we will see again. So for example, I came to know like the class is A. I found what is the network address. So I will come to this particular block and I will find what is the network address. Okay. And what is the next hop? Okay. Like next hop means if this is the router. Okay. This is another router. 2. This is 1. This is 3. Okay. So if I consider from this particular router, I am going to see here what is the next hop, whether it is R2 or R3. Okay. From R1, when I see if I have to go to a particular network, whether the next hop address is R2 address or R3 address, that I am going to have here. Similarly, I will have numbering here, interface numbers. Okay. That interface number also I am going to have here. Similarly, if the address is class B, the same method. Okay, try to find a particular network address and find out what is the next hop and interface number of that particular thing. Similarly, for class E also, we are going to find like okay. So like that, you try to look at this particular method and consider what is the corresponding next hop address and interface number. Okay, is it clear how we are forwarding in classful addressing? Okay. So we are just giving an example here. So if I consider R1, what will be the corresponding routing table? We will see. Okay. So this is class A address, right? And this is class C, class B, class B. So when I look from R1, first in class A, I am going to have information about this one. Okay. So this is rest of the internet. By default, I will be going there. To go to that one, I will use R2. That will be my next hop address. Okay. Okay. Similarly, if I have to go to 170.14.0.0, so this is the address to which we will be giving. Okay, that is the link address, and link number is M2. And if I have to go here, this address, this is the interface address, next hop address where we will be having, and link interface number is M1. And to go to this particular thing, I have I'll give the address of R3. Okay, and M0 is the interface to which I'll be giving. So remember that particular thing and see here. Class A, we are saying class A that is directly connected. So we will be giving to M0. So let's go back. This is class A, right? To go to this network, I have a direct connection. I do not have any intermediate routers, and interface is M0. So we are saying like I have direct address, direct connectivity. So next hop I am not writing anything, but interface I am saying like M0. Class B you have two respective interfaces. See here, class B, this one and this one, they are also directly connected with R1. So I am directly writing the addresses and interface. But when I have to go to this particular thing, I have another router in between. Okay. Next hop address, I am going to keep the address of that router. Okay. To go to this network, this is the address of the next hop to which I will be contacting. Okay. Default, this is the place where we will be giving. Okay. So that's what, like if I have to go from here to here, we will be going to this router, and the address we are giving to that thing is this. Okay. So like that, we are writing this. Is it clear? So in exam, they can ask like they will give some diagram, and they will ask you to come up with this routing table. Or reverse also they can say. This is the routing table I have. Come up with corresponding diagram. Okay. Okay. Router R1 in figure, like whatever the figure we consider, in that one receives a packet with 192.16.7.14. Show how the packet is forwarded. So first we will see, like I found from the packet like this is the destination address. What is the class of this? Class C. So what will be the default mask? 255.255.255.0, and the network address will be 192.16.7.0. Okay, so let's go back. If that is the network address, I need to give it to this next one, and this is the interface. Okay. So we are finding the network address and we are giving to that address. Okay. So look at this one, 167.24, 160.5, right? Do we have that one here? It is class B basically. If I mask it, you will get 167 point something. Okay, but we do not have that one. So what we have to do? Where we have to give it? Default. Okay, we will be sending via M0. Okay, so when I, this is the one we are getting. When I see in class B, we are not able to find. So we are giving it to this next hop because it has to forward it through default router. Okay, default network. Similarly, in okay, shall we stop or proceed? Stop. Okay. We will consider this in next class.